Okay. Well, you guys, get back to your place. Okay. So, good afternoon and welcome back to the final talk for this summer school, which it actually will be delivered by Kumar Abhinav, okay, from Mahidol University. So he's going to talk about localized behavior of deformed nonlinear models. Okay, Kumar, can you hear me?
Yes, I can. Can you see me?
Okay, if you're ready,
Okay.
please. Yeah,
Yes.
thank you.
So, hi everyone. Hello again. So, I will be concluding the school, it seems, as Dr. Sikaran said. Hope you have learned a few things in this summer school, everybody, and I will be talking about. I started this school with some basic mathematics in complex analysis. So now I'll be talking about something which is based on my own research. It might be or might not be very much related to your interest. It's a very specific area, but I feel that it has a lot of general implications. So I'll try to explain it as widely as I can. So please bear with me. So I guess you can see my screen properly. The slide is visible, right?
Yeah, we can
Okay.
see your skin now.
Yeah.
Yeah.
Yes. Sure. So I'll be talking about some solutions of nonlinear equations. First of all, these solutions have a property of localization, that they appear at a particular point in space and time, and if you go far away from them, so they decay out, they don't exist. So in that sense, they are localized. And I'll be talking about such solutions of nonlinear models, especially some standard nonlinear models which are deformed. Why this deformation is of interest, I'll talk about that also. So let's start. Thank you. Uh, so the talk is designed like this, that we'll talk about these localized solutions which are known as solitons in integrable models. This will be just an introduction, very simple one. There are lots of deep aspects which I'll be missing. You may follow up if you are interested. So it's it is a own subject on its own. Then I'll be talking about deformation effects on solitons, that how you, if you deform in a particular way the system where the soliton exists, how it affects the soliton. Then I'll be talking about a particular deformation mechanism called quasi-integrable deformations. And I will list a few systems, very standard and known, well understood systems, where this particular kind of deformation has been used. Uh, the main example will be the Sine-Gordon model. Then I'll go to nonlinear Schrodinger equation, or NLS. Then KDV, or Kosterlitz-de Vries system. And finally, there is something called a AB system, which is a generalization to the Sine-Gordon system. So I list out these examples and then we will conclude. So at the bottom line, you can see these are the references which actually are my works, which I'll be talking about. This talk will be based on, but there will be lots of basic references throughout this talk. So you may keep note on that. Okay. So what are solitons? So they are actually localized structures that appear in different continuous systems, and they are used and they are useful to many physical systems that we know experimentally. And actually, you are very much familiar with solitons. I'll go to it. So first example is the optical fibers. So solitons are used for communication. And how? So these are actually the people use these pulses of light to communicate. So mostly these pulses of light are actually very well defined solitons. Mostly they are localized pulses, like the intensity distribution along the direction of motion of the signal will be lumped together. Like at some place the intensity will be solid, like very high with respect to the other part, and that high intensity structure will move along the direction of motion. So it is like a pulse, it just hits the target. Then and they are used in all telecommunications devices nowadays, and they have medical use also, and experimentally in optical experiments people use it also. Then in biology, our bodies behave in certain ways that solitons can express them, the localized excitations. So you can see these protein dispersion pictures, or and also in DNA system. So these plots are for protein dispersion pictures. So there you can see that these are actually vertical axis, there is time, and in the horizontal axis it is space. So if you see a diagonal line, that means that, oh sorry, one second, the diagonal line means that that is something which is actually localized in space and time. If you take so you have to visualize it yourself. If you freeze time at a particular instant along the vertical axis, you can see at that instant it will be just a localized position where the matter appears. So that's how actually our proteins in our physical system, they actually evolve. So there are localization of proteins also, and then they can be explained by solitons. Then in condensed matter systems, solitons appear everywhere, mostly in spin systems, magnetic systems. Then in the boundary of the topological materials, they actually represent some mirror systems of gravity. So in the given picture, you can see this is some crystal. You don't need to bother about that much. But the spin alignments in these systems, you can see that they have certain structures, periodic structures. But in the second diagram, the below one, where this LH is written, so LH, when the magnetic field turns on, what happens that some spins align in a finite area, and that structure moves along the given direction. So that alignment is a localized entity, and that is a soliton. So that's how actually spin currents move around physical systems. People use it in advanced technology nowadays, which is possible, and they are essentially solitons. Then another example is the your nuclear systems, where you have these many radioactive objects, excited nuclei, which are lumped together. And if you see their distribution, they mostly actually behave like solitons. You can see in the first image in the bottom line, their first image has two lumps. Those two lumps come together in the second image, and the third image they just get separated. You can see the time is increasing uh, as it is written. So there are two lumps which are merging, and they are separating again as two lumps. And you can see the final lumps and the initial lumps, they look almost similar. They just interchange their space. So that's a very interesting property about solitons. Then that if you have more than one of them, they can interact with each other. For a time being, they can become one, and then they will be separated. But after separation, they will look exactly like what they used to be before. Just there can be certain structural reference change, like there can be some rotation, some phase change, but their shape will be the same. So it's a very interesting phenomena that you consider two solid bodies. If you collide them, they break into arbitrary pieces. Like there is no information about the structure before the collision. You cannot say where there are two bodies or three bodies before collision from the information you get after the collision. But here, these special objects called solitons, they not only are localized, but after interaction, they retain their shape. And that's a very interesting property. Like, you can understand that how difficult it is. And there is a certain reason for that. I'll be talking about it. But before that, where this idea of soliton first came, I want to tell the history towards the late part. It is some 150 years ago in Scotland. So, okay, sorry for forgetting the name of the person. So he was, strolling on a horse beside a canal in Scotland. So he just saw a excitation, a structure in the water in the canal, which is like not like a wave. It is not a continuous structure. It was a localized, very localized lump of water which was just traveling along the canal. So that was the first documented observation of solitons. But actually, people here are seeing solitons for millions of years, honestly speaking. Why? I'll just come to that. But before that, in the top picture, you can see some people are in the boat in the canal, and in front of them, there's a line in the canal. So that is actually a soliton. So you can see that's like a wave, but there is nothing like that before that or even after that. And that is moving, because you can see the boat is moving also. So a solid single wave is actually a soliton, what you see in your real life. You have seen it a lot. So in the second picture, you can see there are two lines. Each of them are solitons, and they're interacting. They're passing through each other, honestly. Their shapes will not change. They'll just pass through each other. And honestly speaking, all the waves you see in the sea, they are solitons. Big waves. And in fact, tsunamis are mostly solitons. So these structures are very common in nature. People know it from a long time. And this particular property is that they are localized and they don't change, they don't disperse. They maintain their structure. It was very special, and that's why they were dangerous. Because if a tsunami is created, they will be so stable that if they collide against smaller structures, they don't change. They will stay as tsunamis. So it's very difficult to break away tsunamis, and that's why actually many people die. And I think after 2004, the big Indian Ocean tsunami, people are now getting very much interested about dispersing solitons, I'd say, and which is a very interesting topic, I should say. Okay, so let's go to the mathematics. So by definition, they are localized structures, and they retain shape. So how do you understand that? So let's talk about retaining the shape. So what is retaining the shape means that if it is a localized structure, it does not disperse, it does not spread. So that means that there is no dispersion. Dispersion means the property that a function is spread out with time and space. So for that, for an example, let's consider this equation, which is actually kind of this is the Klein-Gordon equation in 2 dimension. So there you can see it's a wave equation in general. So because second derivatives of 2 different variables, space and time, acting on the function gives you 0. So a standard solution is the solution which is known as the harmonic solution, which has a constant velocity, because it will admit solutions with definite frequency and definite momentum, and the relation between frequency and ratio between frequency and momentum is the velocity, which is constant. So every part of this solution phi will be moving at a constant speed. So at a given time, if it has a distribution, some structure, that structure will not change, because all the parts of the solution will be traveling at the same speed. So it will maintain shape. So maintaining means over change in space and time, it will maintain shape. Okay, just at this moment, I'd like to request you, if you don't understand anything or if you want to know something, just stop me and ask me the question right now. I'm very much happy to explain that. So let's go beyond it. But the situation changes even for smallest, very simplistic kind of properties. Like if you introduce mass to the system, what will happen? The dispersion of the system, the dispersion equation, if you for a given momentum and energy, for this equation. This is the massive Klein-Gordon equation. From there, the dispersion appears like this. So here you can see that what happens, that the velocity will be a series in frequency or in momentum. So it won't be a constant. So because of that, different parts of the solution will be spreading out at different speed. So there is no relation between them, or I should say there is no coherence between them, that they are relatively at the same position. So they will spread out. So the solution of this massive Klein-Gordon equation, they are expected to disperse, that they will spread out. So they will not maintain their shape. And if you bring in interaction, this is a linear equation. There is no interaction. And we know in nature everything interacts. And unless they interact, you cannot observe experimentally. So physical systems that we see in our day-to-day life or in physics experiments, those are interacting systems. And that means you have to introduce an interaction. So that interaction is this last term in the equation. You can see del v del phi kind of thing. So that will be some function of phi. I'm writing it as a partial derivative because, okay, that's the equation of motion, and that's how we define a potential. It's a derivative of the potential that appears in the equation, and that will be in general some nonlinear object. So if there are such interaction comes in, it is almost impossible to get a solution which has a harmonic form, that it's a function of x minus ct. So, okay, what do I mean by harmonic is that x depends, phi depends on position x and time t, but not independently. It depends in a particular combination, which is x minus ct, where c is the speed. In this case, c is the phase velocity, which is if there is dispersion, c is the phase velocity, which is the velocity of a particular portion. You can consider it to be a point of the solution. It's not the velocity of the whole solution, and the whole velocity, group velocity, is some kind of a average velocity, as you know, if there is dispersion. Okay, so the argument is that if there is nonlinearity, harmonic solutions are not available, and that's why the velocity is different for different portions. So the solution will spread out or collapse, but it will not retain shape. So it cannot be a solitonic nature. So fine, but what happens actually in these nonlinear systems, interacting systems, people observe solitonic structure. The water waves you saw or DNA waves, whatever you saw, those are the proofs. So what happened there? Although the solution is not harmonic, it's not directly dependent on x minus ct directly. What happens? The energy of the system, that has a harmonic nature, that can have a harmonic nature. How? So let me define the energy for this phi 4 interacting system. So this is the energy, and this phi is not a harmonic solution. It cannot be a harmonic solution because there is interaction. But this energy functional, because it's an integration over x, it has a property that it vanishes if the solution vanishes. So that means the energy itself cannot exist without the solution. And you can see this functional has a minima at phi is equal to 0. So if phi disappears asymptotically, you consider that phi, although it's stable or not, like it may not be a solitonic, but the structure is such that at infinity phi dies off. So infinity there is no solution, and physically we expect that, right? Because our physical systems are not infinite, so you don't expect any solution at the infinity, even in quantum mechanics. So if that is so, that means the energy will vanish also at infinity, because the solution vanishes, because phi is equal to 0 is the minimum of the energy. So that's why this energy itself, or rather the energy density, so whatever inside the integral, the integrand is the energy density, that kind of it has a localized behavior. And if it is possible to write down the space-time dependence of energy density, this epsilon, as x minus ut, where u is some constant parameter, It may not be the velocity in that sense, but it might have dimensions. So if you can write down the energy density like that, that it is a function of x minus ut, it does not depend on x and t separately, then you can actually have a localized excitation. See, here we are seeing energy and field as complementary. Like if energy is localized, the field has to be localized, because energy cannot exist without the field, because energy vanishes when field vanishes. That is the important thing here. So you can, if you cannot, you have difficulty in tracking the field, you can keep tracking the energy. And if energy has such a dependence, that means energy is localized. That means the field distribution will be localized. So it will be a solitary wave. Okay. So it's the same concept that you have a harmonic kind of a behavior, but in terms of energy, because you cannot keep track of the field very easily because of nonlinearity. So it's a very clever trick in that sense. And in general, for interacting systems, people define solitons in terms of energy because of that thing. And people who have done classical mechanics, I think you have done it well. So you know tracking energy, that means the Lagrangian formalism is easier, or for Hamiltonian formalism is easier than doing Newtonian mechanics from anybody or interacting or field theoretical systems. That's why we do Lagrangian formalism, because Newtonian mechanics has this force, which is a vector, which is very difficult and which is pointwise. So we talk about energy, that's why, which is a scalar. So coming back to this concept that energy signifies localization, and it is possible to have localization in nonlinear systems. So that means asymptotically the system is free, only the locally the interaction exists, and you have lumping of the matter at a particular position. Okay. So what happens that you can have this situation in a multiple copies, like in the system, the energy can be lumped at different places. So you can see there is a summation here. So that means the same situation, that these kind of energy lumps appears everywhere, and they may be distributed at particular positions. And they were distributed like that independently, say at time t is equal to minus infinity, long past. And if you get a situation where in the long future at t going to infinity, positive infinity, if you have certain similar kind of energy clumping, but maybe this delta I means a constant shift in the argument, so it's actually a phase shift. So only that change appears, but the energies are still lumped together and lumped separately, and they are separated, individually separated, these energy lumps. Then they satisfy this robustness of soliton also, that even if there is some interaction at some finite t, long before and long after, they are well separated, and then they maintain shape. So these are actually solitons. So that's how we interpret solitons robustness in terms of energy. So they maintain shape over collision, and they are localized. So what happens in this nonlinear systems? Actually, it is says that see, the nonlinear system has two aspects. First, there will be some dispersion because of the dynamics. So the solution tend to spread out, and there is another effect, which is the nonlinearity. Nonlinearity means like that phi square, phi cube, or something like that. So physically, that means that the system tend to lump together, like one atop the other kind of thing. That you have multiple phi's. You can imagine multiple phi's at the same position. A term means that what that means, that you are lumping together. That if even if phi is small, phi is like say 1.2 or something, if you define phi cube, that is like near about 2, so it increases. So this lumping together behavior of nonlinearity, that represents a tendency that the system wants to come closer, but because of the dynamics, the kinetic part and all, it wants to spread out. So these two tendencies compete with each other, and when they balance each other, spreading out and lumping together, they balance each other. They have a stable structure, and that is the soliton. That's how we understand solitons physically, that dispersion and nonlinearity cancels each other out, and they have a stable structure. So the mathematical mechanism that handles all evolution of nonlinear systems is, one of them is the Lux method, which is very widely used. So Lux method is actually mainly used to represent solvability of the system. So I will not prove the theorem. It's actually not possible to do it here. That if you have a system, a continuous system, and you can define a Lux pair, in general, it is said that once you can define a Lux pair, the system is solvable. Or you can define a Lux pair only if the system is solvable. So we'll go to it directly. So solvable means actually integrable. Why? Because these are differential equations and you have to integrate it to solve it. So that's why they are the same thing, integrable or solvable. But remember, these are infinite degrees of freedom system. And what happens, solvable means we can figure out each and every degree of freedom. So if you can determine, that means you will measure and you will get some quantity. So that means there is some conservation. That's why you are getting a definite quantity under measurement. Otherwise, it will be different. So those conserved quantities are called charges. And for infinite degrees of freedom, if it is completely solvable, there will be infinite number of charges. And you know Noether theorem, which says in continuous system, if there is something conserved, there is a symmetry along with. So there are actually infinite symmetries in the system. So everything, all this is represented by the Lux pair. So it's a pair of operators, say L and B here. And the equation of motion, whatever equation you have, the dynamical equation, is represented like this, that del L del T is equal to B L commutator. This commutator can be, in classical system, it can be the, like in quantum system, it is the commutator. In classical system, it can be the Poisson bracket also. So that is the equation of motion. So given different Lux pair expression, you can generate different equations, proper equations from this Lux equation. But more interestingly, this one of the Lux operator L that evolves in time unitarily. So it's a unitary evolution. Like what happens in to the observables in quantum mechanics, like Hamiltonian or momentum, they are unitary operators. So they evolve with a operator U, which is unitary in that sense. And you know, if there is a unitary evolution, you can actually construct infinite number of quantities like this, that any power of such operators, its trace will be time independent because it evolves unitarily. So so you just define the trace of some nth power of L, then you take the involution, and you know, inside the trace you can change the order of the operator cyclically. So you can change the order and keep on cancelling U with U inverse. So finally you will end up with L to the power n, but at time is equal to 0, or for that sense, for at any particular time of your choosing. So in this expression inside the trace, so U L U inverse, then following by U L inverse. So U inverse and U cancel out each other, and the U's at the end of the expression, because of cyclicity, they will cancel each other out, because that is a property of the trace. So L and different powers of L, they represent conserved quantities, and on principle you can construct infinite number of them, because n can be anything small n. So you have infinite conserved quantities, and obviously Noether theorem, because it's a continuous system, you'll end up with conserved quantities. So finally, there is something called Liouville theorem that enables you to construct make these conserved quantities as canonical momentums, which will have correspondingly cyclic angle variables. So that means if there is something conserved, cyclic means the system does not depend on those corresponding variables. The momentum is conserved. So remember, these are canonically generalized momentum. They may not be the physical momentum you see. There are certain variables just that. But you can formulate by taking them as momentum. So each of them are individually conserved because they are independent of each other. If you see their bracket vanishes, that's why you can define individual energies which are conserved independent of each other. So if they're individually separated and conserved, they will stay conserved for the whole span of time. That's why they represent individual excitations, and because they don't depend on the position, they can be localized anywhere. So in that sense, they are solitons. And we see solitons appear in this formalism like this, and automatically they represent infinite restrictions. Like you have infinite conserved conditions, so infinite restrictions. So here also you end up with localization. So in Lux approach, it is the infinite restrictions that results into localization, and that's how the solutions can represent solitons. So Lux formalism is used to handle continuous systems which have localized excitations actually. Okay, so with this knowledge, we proceed for particular systems. So just as an example, what are Lux pairs for different things? So this L operator, if I expand it as partial derivative of x minus some A operator, just a way of writing, you can write down this Lux equation, or that is the equation of motion. If you remember this equation I was talking about, yes, this Lux equation here, del L del T is B comma L, where L, if I replace as delta x minus A, then this equation itself, which is the equation of motion, can be expressed as this, that time derivative of A minus space derivative of B plus A B commutator, that will be 0. That is the equation of motion. And if you know something, and I think you have learned it in the school, something called gauge theories and all, you know this is the expression of the curvature tensor. So in case of Maxwell's theory, it is the electromagnetic field strength, and in gravity it is kind of a toned down version of what you known as Riemann curvature. So this curvature vanishes. Mathematically it is called curvature, but for us it is some quantity defined like this. It is 0. So it is called as zero curvature condition. So zero curvature condition means it is the equation of motion, nothing more than that. So if the curvature vanishes, we say the system is integrable. And from now on, people may call A, B as the Lux pair, or you can call L and B to be the Lux pair. They are equivalent, you can understand. So for example, I'm listing out different systems and I will go into them individually. Like the KdV system, it's a famous equation where you can see it's a third order differential equation. So the Lux pair is given like this, L and B. Then there is this sine Gordon system, which we will explain in detail. So there is del plus and del minus of u. So what is del plus and del minus? They are actually partial derivatives with respect to variables which are t plus x and t minus x. These are known as light cone variables, and they are very much used in special relativity. You remember the light cone in special relativity, that is actually explained in terms of these variables. So it's easier for sine Gordon system to use these variables. So under these variable representations, the Lux pair looks like this. And these sigmas, you can see there, are not numbers. They are Pauli matrices. The SU2 Pauli matrices, which represents spin. These are exactly the Pauli matrices. And similarly for something called NLSC, which is the nonlinear Schrodinger equation. So there's the same Schrodinger equation in quantum mechanics, but there's a nonlinear part additionally. So there's the interacting part, which is, you can see it is the Schrodinger equation. That h bar is omitted only, mass is omitted. That's why it looks like this. So this u bar u mod square u, that is the nonlinear part. So it is called the nonlinear Schrodinger equation, and its Lux pair looks like this. So sorry, just there is a notational mistake. This q and q star should be u and u star. I just sorry, left it by mistake. So these are the Lux pairs. There also you can see these Pauli matrices appear, and they will be really important for us when we talk about the deformation mechanism. So they are matrices, so they will have some commutation relation or algebra, and that algebra becomes really important when we deform these systems in a systematic way. So they are these Pauli matrices are known as generators, internal generators of this uh, symmetry algebra of this Lux mechanism of that particular system. So you can see the KDV does not have these Lux pairs. Actually, we can introduce Lux pairs. Does not have this Pauli matrices. We can introduce Pauli matrices inside them. There's a representation like this, but it is not always necessary. But in Sine-Gordon and NLSC, Pauli matrices appear automatically in the definition of Lux pair. That means you can play around with their algebra, and there is an internal algebra of the system. We'll go to it. So now, after understanding these solitons and integrable models and the Lux mechanism, let's go into something called which is quasi-integrability. So the concept is that integrable models are very idealized one. The main ideal aspect is that they are infinite. We consider them to be infinite. That's why we take the limit x going to infinity, t going to infinity. But actually, nobody can access those realms. Like, we cannot be alive till t is equal to infinity. So real systems, they are finite, first of all, but that does not mean they have finite degrees of freedom, because we are going to model them as continuous systems, and even if the extent is finite, the number of degrees of freedom will be still infinite. Remember that. But what is interesting about real systems, that they have irregularities or deformities. What do you mean by irregularities or deformities? We always assume that systems are isotropic or homogeneous, but we know actually they are not. Like, if you prepare a sample of any physical material, it will have some defect, maybe some crystal defect or something. Or if you look at different direction inside the material, there will be some irregularities. They will not look same. So there are deformities in the system. And if you want to represent those that system by integrable model, which have this infinite number of conserved quantities, so if everything is conserved, that means everything is symmetric. How can you represent deformities? You cannot. So that's why integrable models, ideal integrable models, are on principle not suitable to represent real systems, because real systems have deformities. So instead of integrable models to represent real systems, we want certain systems which are mostly integrable, but some charges are not conserved. Partially it is not integrable, like some charges are not conserved. That is one requirement. But the second requirement is that we see localized excitations in real systems, like you saw all those real pictures. So that means, and we understood that, okay, you need infinitely conserved quantities, infinite symmetries to have localized excitations. So what is happening? Or what kind of system we need, analytical system we need, mathematical model we need to represent such realistic systems? So we need something which cannot have infinite conservation locally, because there are local deformities, but there are localized excitations. That means, at least asymptotically, that system, if you take the asymptotic limit, that x going to infinity and t going to infinity, theoretically, if you take that limit, that model should give you an integrable structure, or that means that all charges should get conserved. So I'm repeating again, all the charges locally cannot be conserved because there are local deformities in the real system, but asymptotically all the charges need to be conserved because there are localized excitation in real system. So both these needs should be balanced and should be satisfied, and for that you have to go for a system which has all the charges conserved, but except a subset of them being not conserved, but only locally, and asymptotically all the charges are conserved. So it is something like that. You can say that the system is not integrable locally, but asymptotically it becomes integrable because all the charges are conserved asymptotically. So that's the notion of quasi-integrability. So such systems are known as quasi-integrable. that the charges are not all the charges are locally conserved, but asymptotically they may be conserved. And we'll see it happens under certain conditions, certain symmetric conditions the system needs to satisfy, that all the charges are conserved asymptotically. And in the formalism, we use the Lux technique, so the Lux pair equation, Lux equation. And because the system is not completely conserved, you expect that the Lux condition is not satisfied. So the zero curvature condition is not violated. You expect that locally, but asymptotically it should. So, okay. So as a concrete example, the way it was introduced first in 2011 by Ferreira and other people, that they considered the Sine-Gordon system. And the Sine-Gordon equation, again, I'm reiterating, it is in terms of light cone coordinates. Like it has the nonlinearity is in a as a sinusoidal function, and this is the equation of motion. So at the level of energy, you can define a potential, which is this. And you know, if you take a derivative of this potential, it will end up giving you the right hand side of this equation. So which you expect. So the potential is something like it's a cosine function, and this model itself, this equation, you can check it satisfies. It is satisfied by something called a kink soliton. What is a kink soliton? I'll show you just in the next slide. So it's a solitonic solution which is localized. So okay, it is an idealized system. There is no deformities and all. It's an integrable model. So it satisfies. It is satisfied by solitonic structure. Okay. So before proceeding, Sine-Gordon system is actually very important. Like it appears in everywhere in nonlinear dynamics, in quantum field theory. It represents many collective modes in known systems. Then in condensed matter, like in crystal dislocation, Josephson junctions, charge density waves, phonon mode excitations, and even in biology, in DNA double helix dynamics, it's used everywhere. So it's a very important equation. So that means if I deform this equation and get some meaningful solutions, that means those solutions should be physically observable, and people have observed these things. So let's proceed. Let's see that how you can deform this system. So the deformation is like that introduce a parameter epsilon like this, and you can see if epsilon is equal to 0, you get the undeformed system automatically, no problem. So the potential is kind of deformed like this. I hope you can see this. So this solid line is the undeformed potential, and these dotted lines, two dotted lines, are the deformed potentials. So therefore epsilon values, I guess plus 0.5 and minus 0.5, just a small deviation. And that is given by, this is from the paper of Ferreira. So you can see the essential nature of the potential actually remains the same upon this deformation. But you might think that epsilon being small, it's a perturbative effect. And so we should get roughly the same shape. But remember, these are nonlinear systems, and these are not just linear approximation. So even if epsilon is small, its effect can be greater because it's a nonlinear system, and it's highly infinitely nonlinear because it's a sinusoidal nonlinear kind of thing. So even if epsilon is 0.5, the effect can be very great also. So these are actually non-perturbative behavior, although epsilon I am taking just 0.5. If you take epsilon to be 1 even, which is like considered to be large, the deviation is not enough, not much, like the essential shape remains the same. So okay, so this is a non-perturbative kind of deformation that I wanted to convey. So the solution, the king solution that you saw, this arc10 of alpha x minus vt, which is localized because it's harmonic, you know that already. And this, this delta and alpha are some constant parameters. They are in general some phase and factor parameters, so they're not that important. So the kink is actually looks like an S. Asymptotically, this will go to whatever be this height. After this point, it will remain the same. It's constant. And this side is also in the negative side also it will remain constant. So that is a kink actually. So this is like a smoothen out step function, nothing more than that. But that step itself, the position of the step is localized. So everywhere the function is linear, just a flat line, but at the exchange point, it's like a step. So it's a localized structure. That's why it's a soliton. So it's known as a kink. And if you get it in an opposite direction, it will be called an anti-kink. Okay, an opposite S. So in that sense. So the solid line is the undeformed one, and the dotted line are the deformed one, corresponding to the same parameter values as the potential. So what happens that they don't differ that much. So still you obtain a localized structure, and that means under this particular deformation you can still have solitons because you have localized structure. Just there will be some local deformation. So it's a good sign. I'll talk about the mathematics, but they have calculated it numerically, and it's a direct signature that you can have localized structure, you can have solitons even if you have done a non-perturbative deformation. So it was a very interesting thing that although the system is no longer integrable, it has a partial integrability, and the deviation is only local because asymptotically the system goes to integrability. Okay, so the mechanism itself, the mathematical mechanism is that this partial conservation, if you can show through a mathematical process called abelianization, for which you remember I talked about these gauge fields, connections and all. And okay, once again, let me go back. Yes. So at the top line, you have this zero curvature condition. So A and B commutator, it's like a nonlinear term in A and B, right? The first two terms are linear in A and B. So this A comma B, this represents actually the nonlinearity in the system. So if that nonlinearity is not there, you have integrability. Even if there is no zero curvature condition, because it's a linear system in that sense. You'll say, sorry, you will have localized structure because it's a linear system. So if there's a mechanism that I can separate out the system in a way, I can show that there's a linear representation, that I can get rid of this commutator bracket. So I have a linear system and I can show conservation. At least I can calculate things easily. So that is the procedure used, that okay, you want to linearize this equation, so you want to get away with this commutator. So if the commutator is present, this is called non-abelian because there is a non-trivial commutator. So we want to abelianize the system. That means we want to make this commutator disappear. So that is called abelianization. So that abelianization procedure is used. Like you have the zero curvature condition, which has a non-abelian part, the commutator. You want to get away with this. For that, we'll use something called a loop algebra, which is constructed from generators. Which are the generators? Those Pauli matrices, for example, you remember from KdV equation and Sine-Gordon equation and nonlinear Schrodinger equation. Those Pauli matrices are the generators. From there, we can construct a loop algebra, and we'll use that loop algebra to create a linear connection or linear curvature or a abelian curvature, which will automatically give us a continuity equation. That we'll see. You remember the continuity equation has a space derivative and a time derivative linearly acting, right? So the Lux equation actually looks like that, apart from the commutator. So we have to get rid of the commutator, practically meaning. So for that, can you do it always? No, you cannot do it always. But if certain condition is met, that there is a constant semi-simple element of the so-called loop algebra constructed by the generators present in the Lux pair, that can separate the group space in distinct subspaces, mainly kernel and image subspaces. We don't need exact definition. We just need that there are two subspaces in the group space. I'll just show you an intuitive way to mark them. Then you can separate out the linear and non-linear part into different subspaces, and you can work in one particular subspace, maybe the linear subspace. So your system becomes abelian, and because it's linear, you can have a continuity equation and you can define a conserved charge. Okay, but for that you have to do certain gauge transformations, because these are basically, it's a connection, that means those are gauge fields. You can do gauge transformation, gauge freedom is allowed. So doing those gauge transformation will go to a linear subspace. So on principle, so these are all catchy words for you, but how to do it, I'll show you as an example for sine-Gordon system. So in the sine-Gordon system, the Lux pair, what Ferreira et al. Gave, the Lux pair looks like this. So this A plus and A minus are the Lux operators. So they have these expressions, and these F1, F0, B1, B minus 1, all these are loop algebra generator constructed out of your Pauli matrices. Actually, at this level, these are only Pauli matrices. Just the labeling is different. You may go through their paper to see what they exactly are. So in the red, I am marking this B1 operator with a coefficient, and V is the potential. So there is no derivative in there. So your B1 is actually that semi-simple element of the algebra with a so-called constant coefficient. Constant means actually no derivative coefficient. It's actually the potential. It's actually a variable coefficient, but constant in terms of derivatives. So if it is something like that, this element, if I can identify this element, I can do abelianization. How? The SL2 loop algebra, which is characteristic of this sine-Gordon equation, satisfy this commutation relation. These three commutators are non-zero, others are zero. So you can automatically see that this B operator maps F odd operators to F even operators. So you can see 2n plus 1 is odd, then 2 in bracket m plus n plus 1 is even. M and n are integers. So you can see that B operator maps F odd and F even to each other. So if you start with F operators, some combination of F operators, and you take commutators with B, you will go to combination of F operators. So these F operators, they construct something called the image subspace, and B construct the kernel subspace. So they are actually separated from each other because these generators are linearly independent. And from this algebra, the commutation relation, you can see that B maps F image to image, and when you take FF commutator, you take commutators from image space, you do group operation in the image space, you get mapped to the kernel subspace, which is represented by the B operator. So that B operator kind of, it's alone, it represents the kernel subspace, and it appears as a particular element without any derivatives in one of the Lux pairs, one of the Lux operators. So that actually helps us in doing this abelianization. So how to do it? Before going that, you notice if I start with this Lux pair and I calculate the this curvature, it is not zero. So it will not give me a zero curvature condition. So the equation of motion does not satisfy zero curvature condition. That means it is not an integrable system. Obviously, it is not integrable because in case we do a deformation, the way we did the deformation of V, that will keep a non-zero right-hand side to the curvature. So this curly X symbol, which is represented like this. Remember, this V everywhere is the deformed V that we had. This is non-zero unless you make this epsilon is equal to 0. You remember this epsilon when we had, yeah, this epsilon. If you put this deformation parameter, then the curvature is not 0. If you make this epsilon is equal to 0, the curvature vanishes and the system becomes integrable, which is the standard sine-Gordon system. Okay, this is the mathematical form of the curvature. Not that important for us right now. It is called anomaly. This F1 is the generator, so the functional form is known as the anomaly, which is the non-zero part. Okay, so how to do abelianization? I say you do a gauge transformation. Obviously, there is a gauge structure. You can do a gauge transformation because there is a definition of a curvature. So you take these A plus minus generators, which can take values plus and minus, and you do a gauge transformation by defining a gauge operator called G. And you can see standard gauge operators are defined as exponential something, but it is a combination of only F operators, which are the image operators. There is no B in G. So you know F takes a commutator with B, it will create an F. That is the algebra. And F takes a commutator with F, it will create an B. So, okay, let me reiterate again. So, FF commutator gives you B, and F commutator with B gives you F. So, there's a clear-cut separation. So, we'll use that property. And you take this gauge transformation and choose this expansion coefficient zeta n such that after rotation, the minus component of the after gauge rotation, the minus component of the gauge operator will become dependent only on B operators, or that means it will be restricted to the kernel subspace only. So A minus operator becomes confined to the kernel subspace. So small a means after gauge rotation. So if you remember before, A plus had the B1 element, the kernel semi-simple element. It is called semi-simple. So, but you make A minus, this capital A minus, who after rotation, which becomes small a minus, to be confined in the kernel subspace. You could do it because A plus had a B1. Okay. If you do the calculation, it will be clear. You can see in the paper. It is a long, tedious calculation, but doable in that sense. So what will happen that and A plus after rotation, it's a mixture of F and B. That doesn't matter. But A minus strictly belongs to the kernel. And the curvature itself, F plus minus, which is non-zero in general, under this gauge rotation, it also belongs to the kernel. So one of the gauge elements exclusively belong to the kernel, and the curvature also exclusively belong to the kernel. Okay. So because of that, because the kernel and the image subspaces are linearly independent, the kernel part of the curvature condition after rotation, if you take, that will give you a linear equation. You can see there is no commutator here. Earlier, just let me go back. In the definition of F plus minus in this on-shell curvature tensor, that last line, you can see F plus minus had a nonlinear part, the commutator. But after rotation, that nonlinear part in this first equation has vanished. So we have a linear equation, and we are happy with it. Why? Now you take a integration, space integration over this, and if you do that, you will immediately see that we assume that at the space-time infinities, the time derivatives disappear. Okay, you have to go back to this in the derivatives. You have to change to from light cone to the space-time derivatives. If you want to do it, you will see that obviously the space derivative will disappear because that will be a total derivative, and you are taking space integral. So asymptotically, we assume that all the mathematical structures vanish, fields vanish. So only when the time component remains. And that's why you can define actually a charge like this Q, which time derivative is this. So this is dq dt, which is here. You just compare the coefficient, you will find it. So you can see this dq dt, which is alpha 2n plus 1, like this. This is non-zero, but it depends on this curly x. The interesting thing is that this curly x is the anomaly which vanishes when epsilon is 0. So if the deformation parameter vanishes, this curly x vanishes, and if that vanishes, or chi vanishes, and if that vanishes, dq dt vanishes. So means q is conserved. So these are the so-called quasi-conserved charges which are non-zero when epsilon is, which are non-conserved when epsilon is non-zero. That's how you obtain these quasi-conserved charges. So for that you have to linearize, and linearized you do it through gauge transformation, certain gauge transformation. So you have to choose it judiciously. So fine. So these charges, these q charges, which are infinite in number because n can take any value, they are not conserved locally in general. We see that if epsilon is non-zero, or we consider the deformed system. So okay, we have a system now which have non-conserved charges, but we need asymptotic conservation for it to be quasi-integrable. That's what we physically want, because realistic systems, so local excitation, that means at least asymptotically it should be conserved. So how to see that? For that, asymptotic conservation, what does it mean? That means these charges, although their variation locally is not zero, if you consider the asymptotes at t is equal to infinity and t is equal to minus infinity, they should be the same. That means there is no change among them. Locally what happens doesn't matter, but asymptotically they should be the same. So you have to do one more time integral of this system, because the expression was for dq dt. You take a time integration, so from infinity to minus infinity, and it will give you q at t infinity minus q at t minus infinity, the difference between them, and that should vanish. Okay, and you have to show that explicitly. How? To show that, actually we could use something which is internal to the loop algebra, which is called Z2 automorphism. So it's like a analog of parity in the group space. So all these expansion coefficients, they have definite Z2 automorphism, or you can say group parity kind of thing, that they are odd or even under this operation. And by using that through a kind of a tricky algebra, you can show that this expression can vanish, this whole expression can vanish, given this anomaly x, which is a function of potential, which is a function of the field variable. If the field variable has certain parity properties, even or odd. For example, Sine-Gordon system, the requirement is that phi, the solution, has to be an odd parity solution. So I am talking about parity. It's not a very strong condition. So even very deformed kind of nonlinear systems also, you can have proper parity solutions. And we have already numerically seen that odd parity solutions exist, which are kink. So this structure that you had, this kink structure, the below one, that's a odd function. So odd parity, under reflection it is odd, you can see. So we have a odd parity solution already. So we know odd parity solutions exist. That means these charges can be conserved asymptotically. That means the system can be integrable asymptotically. So it's a quasi-integrable system, what we physically require. So kink exists, that means it is quasi-integrable. It is not integrable because there is no local conservation, but asymptotically it is conserved, and it is asymptotically conserved for kink solutions or particular parity solution. There are other solutions, other odd parity solutions also, localized solutions, for which it's conserved asymptotically. So that means particular solutions can exist in that system which are localized, for which the system can be quasi-integrable. So that means the system can support these localized solutions or solitons. So you can observe solitons in these deformed systems also. So these are the numerical results, more that I want to give it to you from this Ferreira and Zakrzewski JHEP paper in 2011. So these are the so-called dark and bright soliton solutions which are possible there. So even for some even parity solutions were there also, which are actually discarded because of this parity conditions. But you can see these are the odd parity solutions. So in the second line and third line, these are the odd parity solutions, but they're deformed. They are not very very distinctly symmetric in that sense. So under certain conditions, they are exactly odd parity solutions, and that's why they give you quasi-conservation. So such odd parity solutions are available, and for that particular solutions, the system is quasi-integrable. Or rather, these odd parity structures are actually solitons. So you can see such structures. So that means in real life that non-conserved systems we have, that can be modeled by quasi-integrable models. So quasi Sine-Gordon system can represent a real life system which have local deformities, which is actually the physical cases. Okay, so we actually introduced this model to supersymmetric Sine-Gordon model. So this is the expression for supersymmetric Sine-Gordon model, where actually the variables are there are 4 variables, because this is a supersymmetric system. So you have supersymmetric parameters theta additionally. So it's a extended system, and what we could show that, okay, they can also display quasi-integrability, because this abelianization procedure passes through very easily, and all those things are satisfied. And because it's a bigger group space, there are 3x3 matrices, not SE2 Pauli ones. They show certain internal structures which are higher order twisted algebras are shown. So basically, there are more commutators, which are not only 3 that I showed you for Sine-Gordon, and they give you beautiful structures, but those are of mathematical interest. But that means there are some extra internal symmetries in the supersymmetric extension. So now let's talk about one more example. I have only 2 examples left. I'll just mention them because I have told you about the mechanism already. So this is the nonlinear Schrodinger system, which is very much useful in physics. In optics, it's used a lot. Then in condensed matter, superconductivity is given by the famous Landau-Ginzburg equation, which is a nonlinear Schrodinger equation. In optics, you have this Gross-Pitawsky equation, which is a nonlinear Schrodinger equation. In fluid dynamics, nonlinear Schrodinger equation is used directly. It is used in animation also, to show you water waves in all the animes, or the motion of hair of a girl in when air blows. So they solve nonlinear Schrodinger equation. So it's very important and very common. And nonlinear Schrodinger equation represents supports a lot of solitonic structures. One of them is this so-called bright soliton. It's a single soliton structure, which mostly looks like sec hyperbolic kind of. So this is a time versus space. Means space time is a 3-dimensional plot. The soliton looks like this. Just it's a local hump, nothing more than that. So its deformation was again done by Ferreira et al. Same mechanism, the Lux sphere mechanism, and they deformed the. See, you remember the NLS potential interaction is cubic, q square q kind of time, q mod square q kind of thing. Q is complex, so its potential has to be quartic. So you deform q mod to the power 4 is the potential, and quasi deformation is that you do an epsilon deformation of this form. You just do it. And the single soliton solution that actually gets deformed, you can see this soliton is uniform and symmetric. Here the solution is antisymmetric. So this is the bright soliton solution, the first one. The second one is the dark soliton solution. It is just the opposite of the bright soliton. You can see the deformed version is also exactly opposite. And there are some localized spike kind of things. So these are very close. Actually, it is not one spike. There are multiple spikes. So they appear in quasi-integrable excitation, not seen in the real analysis system. So these are the additional localized solutions that the system satisfy. It is quasi-integrable. It is not integrable. It may have some different localized structures also. So these are numerically observed. Then what we did, we tried to see the internal structure in a way that can we get more solutions. Like we actually you see the soliton is a complex soliton. We can separate it in real and imaginary part. So the real part, at least I can show you the space and time dependence, that actually if you vary this variation parameter epsilon a lot, say I'm varying this epsilon parameter from 0.1 to 2. So 2 is not microscopic. It's not a small parameter to expand. It is macroscopic. So even though you can see the basic structure remains the same and deviation is not much. So this quasi-integrability, quasi-deformation actually leads to solutions which are very much near line of the undeformed structure. So you expect the deformation of the system to stay close to integrability, That means quasi-integrable. That asymptotically you see all of the solutions, they merge with the undeformed solution. So that means asymptotically at least the integrability nature comes back, or the charges are conserved. Okay, so let's go to this KdV equation. I mentioned it you again. So KdV is used to explain shallow water waves. So KdV is very extensively used to explain sea waves, like when the seawater approaches the shore, it's a shallow water. So it's governed by the KdV equation, and mind you, it's a third order differential equation. So it doesn't have this kinetic kind of interpretation, because Newtonian dynamics works in second order differential equations, Lagrangian also. So it has a lot of solitonic solutions, like this is the one soliton solution, then you have two soliton solutions, these two solitons collides and separates, also maintaining the shape, and lots of them. You can find the KdV solitons cartoons in online, so they will show you the dynamics. So yeah, this is a very good example. You see these square patterns, this tile pattern in the ocean. It is in Italy, I guess. It is in the Mediterranean Sea. Oh no, not Mediterranean. It is, I think the photo is Adriatic. It is in the Adriatic Sea. So this is a real picture. These are solitons. So all these lines, you can imagine there to be solitary waves, and they are overlapping with each other. And because this square pattern maintains, this mosaic maintains, that means they're stable. After collision, they don't change their shape. And atop that, there are some breaking waves also, you can see. Still, they're maintaining their shape. So you see how wonderful it is that these robust solitons exist. And these kind of solutions are actually explained by the KdV, because near the shore it's a shallow wave, not the nonlinear Schrodinger equation, but KdV. NLSC works in non-shallow water mostly. Okay, so but the problem is that it's a third order differential equation, so there is no notion of potential as such, and there is no notion of kinetic part and kinetic part and potential part. So the interpretation that we introduced, something that you don't deform the potential, rather you deform in terms of the Hamiltonian, because still you can define a Hamiltonian. Actually, there are two different Hamiltonians for KdV. We choose this Hamiltonian and you can deform it. If you deform it, I won't go to the detail. It is exactly the same. You define the Lux pair. You do use this loop algebra in KdV, because you can introduce loop algebra in KdV also with generators. You have this abelianization. You obtain quasi-conserved charges that I showed you. So you arrived at certain structures, like the first one is the undeformed soliton, which is the KdV soliton standard, which is a form of sec hyperbolic square. Remember, NLS soliton was sec hyperbolic. KdV soliton is sec hyperbolic square. Okay, both are bright solitons. But after deformation, like epsilon being 0.1 divided by 3, it will have certain structure. For 0.2 divided by 3, it will have this structure, and so forth and so on. So these are very irregular structures. They might not have definite parity structures which are needed for quasi-conservation, but they're very much localized. So the localization will prevail. So in that sense, quasi-conservation is possible in this standard way, the Lux pair method I told you for KdV equation. The point is, people have numerically tried to find solutions. So in the numerical solutions, you don't apply quasi deformation. You just take the deformed potential and feed it and try to find out solutions with boundary conditions. So numerically, these people obtain the localized 3 soliton structures. They obtain 2 soliton structures also. So actually this soliton exists, but in the quasi-integrable formulation, we could not obtain them directly yet. So the research is going on. But there is an equivalent method. I will not be going into it, which is called Riccati type pseudo potential approach. In that approach, actually, you can find out infinite many charges, and they could show non-local conserved charges, basically quasi-integrability, but in a different approach. So it's a research still going on, but analytically nonlinear solutions are, local solutions are very much possible, and they're very likely to produce this wave, this quasi-integrability behavior. The asymptotically the system is integrable. Okay, so I'll end with something which we did recently. So there is something called the AB equation, which is a pair of nonlinear equations. So there are two field variables A and B, which represents two layers of fluid flowing atop each other with different density, like oil and water. And real systems have actually such kind of structure. You know, ocean currents, they have this warm water and cold water layers. And whenever a big river like Amazon mixes with a big ocean like Atlantic, they have this different water densities. They overlap with each other. So certain those kind of more realistic systems in sea current and all, those are represented by such an equation which represents two layers. And such layers actually, when under gravity, if those layers move, there is something called baroclinic instability. So in the interface of these layers, some wave forms, wave motion forms, and those are known as baroclinic instabilities. And there are solitons, localized structures, robust structures that do not dissipate away, that people have observed. And we want to, they are modeled it, model like AB system, which is an integrable system. But we want to introduce the deformation, which is the quasi deformation, because those solitons are not exact solitons. They are some deformations. So physically, atmospheric science also, in the air also you have different density layers. So in geophysical flows like lava and tectonic plate flows, those are actually semi-fluids. Those are not hard plates. So there also this system is applicable. More interestingly, this AB system is a generalization of the Sine-Gordon system under these definitions, and Sine-Gordon is both integrable and quasi-deformable also, with definite solutions we have seen. So we expect AB system to give similar results. So many people in AB systems, they did numerical studies and they found localized structures. So this is a T versus X kind of a plot. So this is for A variable. A variable is complex, so the amplitude is plotted, and there is for B variable also. And you can see these are, if you take a time slash, this is like a two localized excitations. So it's a solitonic structure, and they evolve. Their shape changes maybe, but they stay localized. So approximate solution solitons exist, and two soliton solutions, which are absolute solitons, they also exist, and they also interact also. So these are for A and B. So people numerically obtain this for AB system. But what about the physical systems? So people do experiments. So they have these two layers of fluid of different density, and they take some pistons to disturb that system, and they create this hum sequence. These are small excitations which are solitonic. So what experimentally they observed, they plotted against a sec hyperbolic square kind of thing. It almost matches the sec hyperbolic square structure, which is a KdV soliton. But you can see at the boundaries, they have certain deformities. They move away. The experimental dots move away from the solid analytical curve. So that means the actual system can be a deformation of the AB system. This is always the case. And these are the moving soliton structures that at different time slash, you can see that, or positions, that people are changing the piston, and like it's a composite system. So all these spike excitations, they move around, they come together, they pass through each other. So they have solitonic behavior. So I have given this, this reference. You can see through it. It's actually, they wrote a book also. If you are interested, you can see through. So what we did recently, that we did a quasi deformation of the AB system, which is possible because see, the AB system, if you notice, these are linear, non-linear, but first order differential equation. That's a second order, but you cannot, point out what is the potential or no. But we take a notion, because the AB system is a generalization of the Sine-Gordon system, where B is cos phi. So B is like a potential. B becomes the potential for the sine Gordon system, and A has to be a real function, which is a derivative of phi, if you assume. So B has to be a real function. Sorry, B has to be the potential. And if you identify B to be the potential, you deform B in AB system. And you do all this Lux mechanism of abelianization and you pass through. So we observed an infinite set of quasi-conserved surges, and we could do this loop algebra to show definite parity of these expansion coefficients and the anomaly, so that for particular these localized solutions for definite parity, you have quasi-conservation. So the quasi-integrability of the AB system has been established, and we expect this quasi-integrable AB system to represent these physical solitons, which actually looks a bit deformed from the ideal ones, like this one, like this one, or say this one. This is the very simple one soliton deformed solution. So we could do some direct calculation, not numerical analysis, but direct evaluation of the deformation. So in the left hand side, in the top left hand side corner, these are the localized solutions, undeformed. After deformation, asymptotically the solution kind of deviates from the usual soliton behaviors, but locally it stays a local hump, but the parity property is preserved. So this is for the one soliton solution. Then for two soliton solutions, so these are two dark solitons. The humps are downwards. So this is the undeformed part, the left hand side, in the bottom left corner. In bottom right corner, after deformation, they don't differ that much. The changes happen only at the boundary, but locally they do not differ that much. So they still stay like two soliton solutions, but through a little bit of deviation. And these deviations appear in the same spirit as what they experimentally saw, that at one side the solution lags, it gets dragged, sorry. So we expect it to match with experimental data more than the KdV equation that they used, because the system physically represents a AB system, because it's a two-layer system, not KdV, which is applicable for single-layer shallow system. So I conclude with this, that these are all I discussed about, that quasi-integrable deformation represents realistic systems, and the mechanism is that we use the Lux pair and the internal algebra to linearize the system to find out quasi-conserved charges. That algebra, you have to there is no standard way to find out that mechanism. You have to see each Lux pair for each integrable system to do this deformation, and you have to choose it very carefully. That for KdV system and AB system, we had to choose it very, very carefully to find out the actual operator, to find out the kernel subspace, so that we can map the system exactly. So it may be difficult in some sense, and you have to prove that there are certain algebra symmetry properties under which the charges will be conserved asymptotically. That is under challenge. But if you do it judiciously and systematically, it may be possible for all the systems we know. And those deformed systems are expected to represent real systems more accurately. But in this process, considerable numerics are needed to show higher order soliton solutions, not one soliton, but maybe two soliton and three soliton. And to show their interaction dynamics, you need very high level numerics. And not many people are doing it right now, but maybe people from experiments will be more likely to achieve the positive results. So it's still coming up, it's a new area still coming up, and we see lots of future possibilities for some unknown systems. So let's see what happens. So thank you very much for your patience for 1.5 hours, and I hand it over to the organizers and the students.
All right. Okay. Thank you very much, Kumar. Yep.
Thanks.
Any question from student?
Yes.
Um.
Yeah. Hi.
Okay. So could you hear me?
Yes. I can.
Okay. I just wonder why the sine Gordon equation is so special that they consider the sine Gordon first, I mean they deform the sine Gordon
Okay.
equation first, right? And then they try with other integrable
Okay.
system.
Okay. So there I guess the formal motivation may be because sine Gordon is very important. I told you, in sine Gordon is very useful in field theoretic models. Like if you do scalar field theory and try to find out to analyze physical systems like condensed matter system, if you use this Klein Gordon field theory, its generalization, it is the sine Gordon model which is actually applied to find out uh, collective modes, which are actually not quantum objects. They are semi-classical objects. They are bigger objects. So it's known from some 80 years that sine Gordon equation is very useful in understanding many body systems and all. Now even in biological system also. So that is the formal motivation because it's an important equation. But more so algebraically, I will say sine Gordon is the easiest one to handle this loop algebra mechanism and Abelianization process. Sine Gordon was the easiest one, and you can see their papers or our papers. The shortest papers are for sine Gordon equation. So the equation, so the mathematics was easier. So the first try they did with sine Gordon. That's true. And there was a clear-cut potential in sine Gordon, and sine Gordon is a second-order differential equation, and has certain symmetries. Like it's easier to handle than even nonlinear Schrodinger equation, which is another second-order differential equation. And as I told you, KDV and AB, they are not second-order differential equation. They're it's a bit tricky. So that's why they studied sine Gordon before.
Okay. Thank you for your answer. I have one more question.
Okay.
Um, but I just totally forgot what I'm gonna ask you. Let me recall it a bit.
Okay.
Okay. Um, we we plot the graph with the numerical method, right?
Yes. People try to solve it hardcore numerics. Yeah.
Okay. So
Yeah.
it means that we cannot solve it analytically, or maybe it is able to do it analytically, but it is difficult.
Oh, okay. Yeah. So there are a few aspects to that. First of all, nowadays, actually, the real reason is that nowadays, if you want to, write a paper and publish it, people want you to do it in two ways, totally independently. First, you try to do a analytical solution, find out the analytical solution, and even to plot the analytical solution, you can use some Mathematica or say some other MATLAB kind of numerical support or computers. Even if you cannot do directly, but they also require you to start with a data set, some random data, and the differential equation, and brute force directly to solve it numerically. They want these two approaches nowadays because actually if you can show some results, like those results, like what I'm saying, analytical solution plus a little bit of numerics, if you can solve it directly analytically, give you the functional form, then it is great. But even if it is not, you do some analytical calculation, then do some computer stuff that we did actually, plus you do some hardcore numerics starting with some random data and the equation only. If those results match, you can show, then that is considered to be the the best theoretical way to say that your result is correct. So people do it separately altogether, but experimental thing is totally different. There are numerics involved in there also, but you start with an experiment, not with an equation. So people do it in a three different ways. One is analytical. They do some calculation by hand. People use now mathematical softwares to do analytical calculation. That's a altogether different thing. But I'm saying those are analytic. Then people start with some data set and the equation, which is hardcore numerics. And people do first some experiments. From there, they get some physical data. From there, they do some numerics. So these are three different ways. And people expect that at least you do two of them and match your results. So some of them are depending on the system, one of them can be easier, the other can be difficult. So that is the scenario. So I think you understand now.
Yes. Thank you for the answer.
Okay, pleasure.
Any more questions from students? Well, it seems no. Okay.
Okay.
All
I am
right.
happy that there is at least 1 or 2 questions from one person. I'm totally happy.
All right. All right. Then, if there are no more questions, let's thank Kumar again for this wonderful talk. Okay.
Thank you very much.
Thank you very much, Kumar. Okay. And bye bye. Okay.
Bye-bye.
Again, well, actually, this is the end of the school now.
Yes.
All right. Okay. Bye bye, everyone. From
Bye-bye.
here and from the online also.
Yeah.
All right. Thank you
Yes.
very much. Bye.
Bye-bye.